today we want to ask ourselves is why. Let me just write this question, why, right? Today we're going to ask ourselves a basic question. The basic question is why phosphorylation, right? Phosphorylation sometimes turns on, sometimes it turns on an enzyme, okay? But sometimes it turns off other enzymes, right? Why is that phosphorylation is not working in any sort of universal way, right? Now I think this is one of the most confusing thing in biochemistry, and I usually think that how can phosphorylation activate one enzyme but inhibit other, right? And I think that's a good question. Now we're gonna think about it, right? And I think to understand that we should start building from principle by principle, right? So again, I'm gonna ask you to close your eyes and imagine that I wanna ask you, like, close your eyes and let's say imagine that you are the liver. You are the liver itself, right? Now my question here is to you is that can you simultaneously store glucose, that is increase the level of glucose, and can you break down the glycogen? Can you decrease the level of glucose at the same time simultaneously, right? So we know that glucose leads to glycogen, right? And glycogen leads to glucose, right? So we know that glycogen leads to glucose, right? When you add glucose, right? But when you break down the glycogen, you get less glucose, right? Now the question is, can you do this simultaneously? I think what would happen? Do you think it's useful? I think it's not useful because you just burn ATP while doing this thing, and this is called futile cycle. Okay, futile cycle. Okay, so now want to avoid that, right? So that's why liver needs a rule. The rule is that if glycogen synthesis is on, the glycogen breakdown must be off, right? And likewise, if glycogen breakdown is on, the glycogen synthesis must be off, right? It's an on-off thing, right? So that is glycogen synthesis, right? And that is glycogen breakdown, right? So that's a rule. Now the two main enzyme in this whole picture is first an enzyme that builds the glucose, right? Builds the glycogen, and other worker, that is other enzyme that is that the destroyer of glycogen, right? So we have one enzyme that builds the glycogen, and then we have other enzyme that destroys it. So glycogen synthase is an enzyme that builds the glycogen, right? So simply glucose, glycogen synthase, and so glycogen synthase, that's the enzyme name that builds it. So when glucose interacts with Mr. Glycogen synthase, we get glycogen, right? That's the story. And should the glycogen, what do you think? Okay, so you understand this, right? Hopefully you understand this. And my next question would be, when should the glycogen synthase work? When should this enzyme that is responsible for building your glycogen should go to work? When do you think it should go to work? Well, when you eat, right? Because that's exactly when you have enough glucose, of course, right? And when you eat, what do you have? You have something which is called as insulin, right? So you need insulin and glucose, both of them, for glycogen synthase to work. Okay, now this we understand this. What about if you break the glucose, right? Now if you break the glycogen, right? Now we are gonna break it down. What are we gonna need? If we wanna break it down, we wanna phosphorylase, right? Now how will we phosphorylase? We will first phosphorylase using glycogen phosphorylase, right? Phosphorylase, simply, right? Now the thing that it does is it removes the phosphate from the glucose, right? No, sorry. It I am so stupid. It actually what happens here is that it breaks the glycogen, right? How it's gonna break? So we have glycogen, right? Here is it, glycogen. We have the glycogen, right? Goes through and interacts with phosphorylase, glycogen phosphorylase, right? Interacts with it. What happened here is that we get glucose 1 phosphate. So it puts the phosphate at first position, right? So as you can see, right, what's happening? We have glycogen, and it just destroys the glycogen, and what we get as a result is glucose 1 phosphate. Now we have a phosphate on the first carbon, right? Position carbon, right? Now when should it work? It should work on fasting, that is glucagon, right? That's important, right? So we have these or stress or exercises, right? Stress or exercises, workout I should write. So we have workout, right? Now we have this enzyme, right? We have 2 enzymes of different natures. Okay, now we have 2 enzymes of different nature, and we have glucagon and fasting and this thing, right? So we have this story going on. Now the opposite nature of these enzymes are quite something, right? Now you'll see this. Their nature is quite opposite, of course, right? Because one is building the glycogen and one is not building, one is destroying, right? So their regulation should be opposite, right? So let's understand about regulation, right? So here's the thing. Let's follow the regulation closely, right? Let's follow this. Let's build this slowly. Now we have this enzyme called pKa, right? Protein kinase A. Now it talks to who? It talks to glucagon, right? But it talks via second messenger, that is cyclic AMP, right? Wait, yeah, now it looks pretty. So CAMP actually talks. CAMP is the result of cyclase, right? And cyclase talks to glucagon, right? So this pKa, right, reaches glycogen synthase. This pKa actually talks to glycogen synthase as well, right? So let me build it again. We have glucagon right there, okay? Right. When glucagon talks to adenyl cyclase, right, the cyclase part of adenyl cyclase changes ATP into cyclic AMP, and it happens inside the cell. That is very important. Now this CAMP talks to protein kinase A. Now kinase A means it puts on some phosphate on this, right? It's a kinase. And on what it's gonna put the kinase? It's on what exact material it's gonna put the phosphate on a protein. That's why we call it protein kinase A, right? Now we are at this protein kinase A level, okay? Now it can talk to glycogen phosphorylase kinase, of course. This enzyme will break down the glucose, of course it can. But other thing that it can actually do is it can also talk to glycogen synthase. That's important. So it's gonna talk to glycogen synthase, right? So we have same enzyme, right? Protein kinase A that's kind of destroying the glycogen, and it also also builds the glycogen as well, right? That's the weird thing. We have one enzyme that's regulating both of the things, right? So it's built synthase, it synthesizes, right? Now what's happening here? Now the thing is, should glycogen synthase be active during fasting? Should this enzyme be active when glycogen phosphorylase is active? Of course not. Absolutely not, right? Because the liver is trying to release glucose when glycogen phosphorylase is, when glycogen phosphorylase kinase is active, right? Not store it. Therefore, the pKa, that is protein kinase A, phosphorylates glycogen synthase. Now, question is, what happens? The thing is, it becomes inactive. Now, cool thing here is that pKa, so it's a kinase, of course. So what is a kinase? Kinase is an enzyme that phosphorylates some protein, right? Or some fat, or some, not fat, or some structure, right? Basically. So this one enzyme is responsible to phosphorylate glycogen phosphorylase kinase. That's the first enzyme. And second enzyme that it can phosphorylase is glycogen synthase. Note that in both way we are phosphorylating. In both way we are putting that putting that PO4 negative, that phosphate group, right? And the thing is that you should not memorize this. You should not memorize phosphorylation inactivates glycogen synthase, or it activates, right? You should not phosphorylate anything, right? You should understand about fasting and fed state, right? That's the thing. So now we have this protein kinase A, right? So it phosphorylase kinases, right? Remember that pKa, that is, it phosphorylase kinase, right? This enzyme, the glycogen breakdown enzyme. And so I mean, that's great, right? It's now active, right? It activates this and it inactivates this, right? It has this regulatory thing going on for itself, right? Now that's so amazing, right? It's like one enzyme, it creates two beautiful effects. It can turn on the phosphorylase, glycogen phosphorylase kinase, and it can actually turn off, inactivate Mr. Glycogen synthase, right? Okay, on, off, right? Just one enzyme doing two opposite thing. That is, I think, very cool, right? You don't need like extra switch. The switch is quite intelligent in itself, right? I think it's one of the most beautiful design, I think, right? So next question that naturally comes to my mind is, why doesn't phosphorylation always activate, right? Why is it that how would you know that, okay, this phosphorylation is gonna turn on and this phosphorylation is gonna turn off? How would you know that? That's a good question, right? How would you think about it? Like, hey, this one is for the off, or this one is for the on, right? Now the thing is that we understand phosphorylation in a different way. Phosphorylation just means that we are simply changing the protein, right? Now whether activity increases or decreases depends upon the structure, right? It's like a machine, right? You press one button and it might turn on, but you press another button, it might turn off. Now same thing happening here, right? Phosphorylation is pressing a button on these enzymatic machines, right? So this response really depends upon the type of enzyme which is getting phosphorylate, right? So the rule is to never really memorize any phosphorylation, because if you're gonna memorize this phosphorylation, it's not gonna help you, because it depends upon enzyme to enzyme, right? Phosphorylation, the thing to memorize here is that phosphorylation changes the protein structure and conformation, right? So that's the thing with phosphorylation. Now we have another thing. So a simple rule that you can really just know is that kinase, the word kinase, the enzyme that has kinase in its name adds a phosphate always, okay? That's what you can actually memorize, right? That's how they named it. And the enzyme that has phosphatase in its name, phosphatase, actually removes that phosphate, okay? So this is something you can actually like memorize. Like, hey, want to memorize something, okay, you can memorize this thing. This is hard and fast rule, right? So why do you think why do you want to remove the phosphate, right? Because just imagine a patient is eating lunch, right? Now should the glycogen breakdown continue? No, we want storage, because that's why he's eating, right? So how would we reverse the fasting program? The fasting program is going on. How would we? The evolution was like, okay, we added this kinase phosphate on this enzyme, right? Glycogen phosphorylase kinase. So why not remove the phosphate from this phosphorylase kinase, right? Or we added this, right? So this is another way to stop an enzyme. You can remove a phosphate group as well, and to do that we need a phosphatase, right? So we need something which is called as protein phosphatase. Now protein phosphatase, this enzyme protein phosphatase, protein phosphatase, this enzyme, Mr. Protein Phosphatase. Yeah, so this enzyme, protein phosphatase, actually it removes the phosphate group, right? And it's like a reset button, right? It removes the phosphate from these enzymes and it removes, like, it does it. Now there are like multiple things it can do, right? The cool thing that it can do is, I think it can remove the phosphate group from glycogen synthase. Imagine this is the synthesizing enzyme, right? So what it can do is it can remove one negative PO4 from Mr. Glycogen synthase. So that's cool, I think, right? It can remove it. What else can it do, right? Imagine you remove the PO4, you remove the phosphate from the glycogen synthase. What's gonna happen? It becomes active now, right? Now the storage becomes super duper amazing, right? Because now you must be thinking, wow, what the hell is happening? Shashwat, you are like bad teacher. I'm not bad teacher, I'm just bad at explaining in the morning maybe. So what's really happening here is that we had an enzyme that's called protein kinase A. What it did was it put a phosphate on glycogen synthesis. When it put a phosphate on glycogen synthesis, the glycogen synthase actually turned off. Now we have another enzyme. It's called protein phosphatase. The work of this enzyme is to remove phosphate. So once it removes the phosphate from glycogen synthase, it starts working on. That's how it is. Now that's cool, I think, very cool. So one phosphate can actually change the protein. Now other thing that it can do is this protein phosphate can remove phosphate from glycogen phosphorylase. This guy right there. So what's gonna happen? Imagine protein kinase A turns on the glycogen. So well, if we remove the phosphate from phosphate, it's gonna turn off, right? So it can remove PO4 phosphate group, right, from this too. So it's gonna turn off. So we have again same kind of mechanism here going on, right? Kind of same mechanism that one phosphate can change the conformation or structure of protein, right? Other thing that this Mr. Protein phosphatase can do is it can remove phosphate from phosphorylase kinase, right? And what's gonna happen, right? It's gonna just, this one I'm talking about here, it can stop this as well, right? Now let's look at it. Let's look at the master. Like let's look at the whole big picture, right? The big picture is that when you are fasting, when you have not eaten anything, we have this glucagon that's released by alpha cells, right? Alpha cells have these receptors, right? So you're fasting, so glucagon is up. So glucagon will talk to adenyl cyclase, right? Now this adenyl cyclase, the cyclase part of this whole enzyme is going to convert ATP into CAMP, right? Cyclic CAMP. And when it happens, right, the synthase, so the CAMP later talks to protein kinase A, right? And this protein kinase A now has choice to either turn on the glycogen phosphorylase or to turn off glycogen synthase, right? It can put a phosphate either on glycogen phosphorylase kinase, or it can put a phosphate on glycogen synthase. But the thing is, if it puts the phosphate on glycogen synthase, it gets turned off. And if it puts put PO4 on glycogen phosphorylase kinase, it's like turn on, right? So the thing here is that this is the entire way how it actually works, right? So this is the reason, right, kind of why insulin uses dephosphorylation, right? Why doesn't insulin simply just activates glycogen synthase directly? You can think about it. Because liver doesn't need one enzyme to be changed. It needs that entire fasting program to be reversed, right? So protein phosphatase, right, this enzyme right there, protein phosphatase remove phosphate from multiple proteins simultaneously. So this one enzyme, it removes everything. And this one enzyme, protein kinase A, puts phosphate on multiple enzyme also, right? So it's like efficiency, right? So these two enzymes are regulators, okay? And so yeah, that's important, right? Let's talk about the receptors, right? Let's talk about insulin receptors, right? So we have insulin receptors. What are the name of these receptors? The name of the receptors are tyrosine kinase, dimerases. We have this amazing looking big word, right? That is Mr. Receptor. I'm gonna give it some sort of personality. So this is my receptor for whom? For Mr. Insulin. Okay. So that's my tyrosine kinase dimerases. Right, now it's a receptor. Now this receptor is it's a protein, and where is it present? That's the first question. Where? So it's present on the cell membrane. That's the first thing that you wanna know. Cell membrane. Okay, cell membrane. Okay, it's present on the cell membrane. Okay, and it receives signals basically. Now let's break down the typical word. Tyrosine, what is tyrosine? Tyrosine is just amino. Tyrosine is just amino acid, simply. It's an acid, okay? Okay, so tyrosine is an amino acid. The receptor, the whole thing, right? The receptor phosphorylates what? The receptor phosphorylate tyrosine residue, okay? Unlike glucagon, which is a signaling molecule, glucagon signals through whom? Through CAMP. But insulin uses something which is called a receptor tyrosine kinase. This guy, right? This guy. What it does is it phosphorylates something which is called a tyrosine residue. Okay, it phosphorylates tyrosine residue. Tyrosine residue is another body. Okay, it puts a phosphate on tyrosine residue. Okay. What about this word dimerizes? Now, what does dimer means here? Dimer. Well, dimer here means two. Now, what are you saying, Shashwat? Well, dimerizes means two receptors. Listen to me closely. Two receptor molecules join together after insulin binds. Okay, so imagine you have this insulin here, right? Insulin comes and talks to this receptor and binds with it. Here it binded, right? Once the insulin binds, we have two receptor molecules, this one and this one. They join together. They're gonna join together, and then they're gonna make one. They're gonna change their shape. Basically, that is what here dimerizes means. So two receptor molecules, they join together to make this thing, right? To make this horn. And let me make it better, right? So we have this one, we have this two molecules, right? This is one molecule, this is two molecule. When insulin, right? So this is my insulin molecule, right? Comes and it binds here. So when it binds here, this two molecules, they're gonna change shape and they're gonna become one molecule, right? And this is actually which is called dimerization here in this picture. Okay, so we have this two molecules becomes one, they join together. Here we call it dimerization. Now, why we have these two different in the first place, right? Why do we have these two different signaling molecules, right? Why two signaling systems, right? This one and this one, right? Why doesn't insulin also use CAMP? These are like good questions, right? Because the thing with insulin and glucagon is that insulin is a different molecule than glucagon. Insulin is not like glucagon. Insulin has different effect than glucagon. I will tell you how. Insulin uses different ways to even signal, and glucagon use different ways. It's like opposite effects almost. So they have different signaling pathways, and this is why an independent system for each hormone is important for a better how should I put it, for better fine tuning of the system. Okay, So if imagine a patient is fasting for many days, right? So which pathway? Protein kinase A, phosphorylation, glucagon pathway breakdown, right? This one, this whole thing. And patient B, he just had, what's gonna happen? He just had a big dinner, Thanksgiving. Insulin goes up, protein phosphatase. What's gonna happen? It's gonna remove that phosphate from glycogen synthase. Everything's gonna work, right? So that's how that's how you would answer this question, that how thus you would answer this, how phosphorylation can actually turn on one molecule and it can turn off another one, right? So that's how